So it's chapter 9 here. This structure we can talk about priority queues, heaps, and graphs. Let's review again. Priority queues is based on the priority. When we queue, it's just like queue operation. We have DQ and enqueue. But when we DQ, we're gonna DQ the highest priority out first. Okay. Heaps. We can use heaps to help in implementing priority queues. Heap is just like a tree, a binary tree, which has two properties. One is it always has to be complete, and we talk about complete. The shape that is complete is always look like a triangle or almost like triangle shapes. We're going to talk about heaps in details and then we're going to talk about graphs. So graph is using a lot for, like, if you search something on a GPS, you want to find the shortest path to a destination. This is graph. We're going to implement a graph with which we can look at abstract data type for the graph, look at all the operation of the graph. Like queue ADT is like enqueue DQ, and we can look at graph ADT. And graph applications, look at how you use applications, like implement one apps using graph. So again, PriorityQ is an abstract data type which interesting accessing protocol. Only the highest priority elements can be accessed. Priority queues are useful for any application that involves processing items by priority. And we can look at this also when we try to an application or even the operating system. We use priority queue to look at which one comes first, do that first. So any application that you want to make an order by queue, by priority, instead of first in first out, then use priority queue. So these are the ADT is empty, is full, enqueue and DQ. Enqueue, make sure the exception. If you try to enqueue the full queue, DQ the exception. If you try to remove elements from an empty queue. When we implement this, we have many data structures that we can use, and we learn unsorted list. Yeah, we can use unsorted list to do this, but the problem is too expensive. If I want to find the highest priority, I have to search through the list to get the highest. Before I remove, I have to reorganize my order again, which is too expensive. Array-based sort is also enqueuing it is very expensive. Because whenever you enqueue, you have to find a location to enqueue because it's sorted list. Now you have to insert between and shifting the rest. This is so expensive. This is like linear time. Now, we talk linear is ON, right? If we use a reference-based sorted list, even reference means use the linked list, right? Pointer. Enqueuing again is still ON. BST. We know BST always give you log-in, which is good. But on average, it is log-in. Not always log-in, just on average, depending on the shape of the BST. But heap, we said, is always guaranteed it's going to be log-in. Why? Because we have two properties. One is shape, always a complete binary tree. Okay. And if you don't know what's complete binary tree, just review chapter 8. We talk about that. It's going to be almost like a triangle shape. Now, in order property 2, that's the second property. It has to be in order And in order in this case is the parents, the value of the parents is always greater than or equals to the value of its children. So example of heaps, like I said, this is a complete tree, like almost like a triangle shape. So when it's complete tree, that's why it's always give you log n. When you search, either go to left or right. This is like search in half. So the problem is not about searching for priority queue. When you dequeue, it's going to give you the root, which is only one. Very efficient, right? But it's not only one because we have to reshaping it. So that's why when you're reshaping it, in order to make it in the heap property, reshaping and make it in order, that make it. Reshaping is just take the mouse right up, wouldn't take much. But when you move it down, that's about login. But because you have to, for example, when I dequeue, so this is the heap, right? The parents are always greater than the children. But let's say I start to dequeue. When I dequeue, J is going to be removed. E is going to replace. No longer have node E. Then we have the shape property back. But when we have to move E down, because we want to keep the order property here. The order property means I have to find the one like between EHI, which one is the greatest. We see I is the greatest, so I has to go to the parent instead, because order property means parent always greater than its children. So I is going to move down, I is going to move up, E is going to go where I is, and then we have to move E again because we have to compare between A, F, and E. And we see that F is greater, then F becomes parent and E moving down. So now we have heap back with two properties, with shape and order. So that's how we do dequeue. We are relying on one operation called reheap down. Okay. Now let's look at how we enqueue. Same. We still have to keep the property shape. That means when I want to keep the shape, when we enqueue, always put a new node at the most right branch. That make the shape property fulfilled. So second step, we have to look at the order. So for example, I'm going to add K. So K is there. We know that K is greater than G. To keep the property, we have to move K up. So we just move K up. We call reheapUp operation. So K is going to move to where G is, and G is going to move down. Again, K start to compare with H. K is still greater than H. Right, always compare with your parents. So greater than H, so K is going to move up and H is going to move down. K start to compare it with its root, M. M is greater than K, so we find the right location. We stop. Then we get a heap back. Shape, property meet, and order property meet. So that's for enqueue and dequeue. Now, to implement this, we can either use linked list, BST, or use an array. And we already know that we can use array to make a BST based on the index, right, formula. You can review chapter 8. At the end of the chapter, we talk about that. Now let's look at how we're implementing this. So we're going to have an interface called PriorityQ. We just look at is full, is empty, enqueue and dequeue. And we use the generics. Then this heap can take any type. And one thing that we have to make sure is heap, we always have to compare. The type that's going to use heap has to be comparable. So that's why we use the generics bounded generic type, which is t extends comparable. This is called bound generic type because it's bounded to the object has to implement comparables. So let's review the generics concept, right? So t extends comparable, just like whatever object that's passing in, it has to be a children of the inherit form comparable. Now we make sure that when it's inherit form or the type of comparable, then we know that we can use compare to find a location to reheap up and down. Now we create an array list. This one is using array list to implement last index and max index. Now the constructor just depending on the size when you create. So one thing about this code is they're missing the default constructor. Okay. Normal default constructor just give the size to an array here. Alright, with no parameters. And it's empty. Just look at last index because we initialize to -1 when we first create, and max index max size -1. So if last index equals to -1, then that is empty. As well as last index equal to max size or max index here, it is full, right? Max index is max size -1. Look at how we enqueue. So we pass the elements to enqueue. So check if it's full. Then if it's full, then we throw exception. PriorityQ is full. Else we can start to do increment the index and add the elements at the last node all the way to the right. So which is last index location. So we have elements.add last index, comma element. And after that we have to do operation reheapUp because this elements.add keep the shape property. This will keep the order property. Now reheapUp, we have to look at the algorithms here. How are we going to implement it? We just talked about that. Let's look at it again. enqueue, what we look at is we give the whole and empty elements a placeholder there. We're not putting k yet, but we just use k to compare with g. Now we just move the whole up. So g go down. Start to compare k with h. Move the whole up. H go down. Start to compare whole with m. K with m. And we know that, hey, k is less than m, then whole equals to k. We're done. So let's look at how we're implementing this. So whole is going to be equal to last index. And we say while whole is greater than 0. Because whole is not a root. Last place is going to go is become the root. And root is always at index 0. So while is not a root. And we start to compare. What we want to compare, like I said, we use the index formula here to get the parents. So whole minus 1 divided by 2 will give the parents.